Okay, so talking about the kinetic molecular model of a gas, this is just connecting things that are happening on the microscopic level with the things that are happening on the macroscopic level. So if we have a container of an ideal gas, that means we have some molecules in there. And the molecules, we'll say there's N molecules, which means their number density, that's just the density of molecules per volume, is N over V. That's molecules N over volume V. So when we think about pressure, from a macroscopic pressure, that's the force over an area, but on a microscopic level, that's just collisions between the molecules and the container. Whereas the temperature is due to the kinetic energy of the molecule. So how fast are they moving? How much energy do they contain? Because remember, kinetic energy is 1/2 mv squared. So the microscopic speed of the molecules leads to a macroscopic measurement, which is temperature, and you can just have a thermometer do that. Okay, so remember, both temperature and pressure depend on the speed of the molecules. So when we think about microscopic pressure, like we can think about this wall over here, and there's just a molecule bouncing off of the wall, right? So if you think about this from a kinematics perspective, we have an initial and final position, an initial and final speed. You can break your initial and final speed into X and Y components. And then if we think about the number of collisions as being sort of this equation, which gives us half the value of the number density and then the average speed over integrated over time. What we mean is, so here's the number density. These are all these particles heading towards the wall, right? Because we're not just talking about one particle bouncing, we're talking about many particles bouncing. They bounce back. Right, so this area and the total speeds in the x direction of the area over this little time t, so that's a little bit of time dt. This gives us momentum. You don't have to know all of this, but this is just sort of giving you the idea of where we're going on the microscopic level. So you can see the momentum. You just add this other term where you have 2mv, right? And momentum is, of course, mv. And then force we can get from this as well. So force is just the time derivative of momentum. So we pull that over here. And this gives us a microscopic way of figuring out pressure. And as we said, pressure is really based on the speed of the molecules. So you can see we have the number of molecules, we have the mass of these molecules, and then we have the RMS speed divided by the volume, okay? So this brings us to a question. If you could suddenly increase the speed of every molecule by a factor of 2, what would the pressure of the gas do? So take a second, think about this, answer it, and then we'll go over it. Okay, so this is going to increase by a factor of 4 because remember you have a square in there. If you look at that equation, you're squaring the speed, okay? So that means it increases things by a factor of 4. As for temperature, temperature measures the average kinetic energy of a molecule. Two gases with the same temperature will have molecules with the same average kinetic energy. So remember, at kinetic energy, as we said, is 1/2 mv squared. The average kinetic energy of a molecule is 3/2 RT. Now this has to do with degrees of freedom and all of that stuff. You could also write this as 3/2 with the Boltzmann constant in temperature, where the Boltzmann constant is related to our big R by Avogadro's number. So we're just going from a molar thing to a molecular thing. This is how you change PV equals nRT and all that stuff from moles to molecules, okay? So this is sort of the numbers and equations you need for temperature on the microscopic level. Now, what does this mean? Well, if you set these equal to each other, you can calculate the root mean square speed, RMS speed, by looking at this. So this is just how we get this derivation. This is where this equation comes from. And you can think of it as like, look, this thing is bouncing around and contacting other molecules on a microscopic level. We're not seeing this when we're measuring temperature, we're just getting a number. But when we look at all of these interactions, this gives us basically a sort of average speed. And this also gives us something called the mean free path, which is basically the length of the space between collisions. So how much time are you floating around in your container without running into other molecules? So let's say we increase the speed of every molecule in a gas by a factor of 2, then what happens to the temperature? And that also increases by a factor of 4 because, remember, the speed is also squared. And so we're going to try this problem. Okay, so here we're just going to try out our root mean square speed. So we want to know what are the, and remember, try to do this yourself first, okay? This is mostly just plugging in. We want to know the root mean square speeds of oxygen and nitrogen molecules at room temperature, which we're going to call 20 degrees C. Knowing that oxygen is a diatomic gas, as is nitrogen. And we have this useful conversion of 1 atomic unit, which is 1.66 times 10 to the negative 27 kilograms. We also have the Boltzmann constant that might be useful to know, and that's going to be K Boltzmann is equal to 1.38 times 10 to the negative 23 kilograms. Sorry, not kilograms. Joules per Kelvin. So for 1 oxygen molecule, we know that our mass should equal 32 atomic units. And that's because, remember, we have 2 oxygen atoms that the atomic unit's basically the mass of a proton or a neutron on average. So oxygen is 16, right? That's how many of those it has. And so since there's a diatomic gas, that means there's 2 oxygens stuck together. So that gives us 32, okay? Nitrogen also, you can do the same thing. It'll give you 28. So 1 oxygen molecule has 32 atomic mass units, which is, basically protons or neutrons. They're about the same mass. So in order to get this in kilograms, we just take that 32 and we multiply it by 1.66 times 10 to the negative 27 kilograms per unit. And that gives us a mass of a less pretty mass, right, than 32, but of 5.31 times 10 to the negative 26 kilograms. So this brings us finally to our equation, which is V RMS is equal to 3 times the Boltzmann constant times the temperature divided by the total mass. And this is, remember, the mass in this case for this equation is the mass of 1 molecule, which we just calculated. So 1 oxygen molecule has the mass 5.3 times 10 to the negative 26. Because this is microscopic, it's not the mass of all of the stuff in the jar, it's just the mass of 1 molecule. Okay, so we plug in our values and we get 3 times the Boltzmann constant, 1.38 times 10 to the negative 23rd joules per Kelvin. And our temperature, which is 293 Kelvin, because remember we got it in Celsius, but that's not what we want. And then divided by the mass of 1 oxygen molecule, which we discovered to be 5.31 times 10 to the negative 26 kilograms. Okay, plug all this stuff in. This gives you a root mean square velocity of 480 meters per second, which should be about 1,000 miles per hour. Okay, we can repeat the same thing for the nitrogen molecule, so 1 and 2 molecule, which has a molecular mass of 28 atomic mass units. We just do the same thing essentially where we say 28 units, 1.66. This is, remember, again, the mass of a proton or neutron divided by 1 atomic mass unit. That should give us 4.65 times 10 to the negative 26 kilograms. So that's our mass, our little m. Once again, we know that our VRMS is this equation. This is the one we got from the slide, and it should be in the book as well. We plug in, hang on, move this back over. We plug in, and this should be 3 times the Boltzmann constant, 1.38 times 10 to the negative 23rd joules per Kelvin, times the same temperature, 293 Kelvin, divided by this value, which is 4.65 times 10 to the negative 26 kilograms, which means the root mean square speed is 510 meters per second, which is a little bit faster because, remember, nitrogen is a little bit lighter, so it's about 1,100 miles per hour, okay? And then that's sort of that, just plugging these in.